Hello and welcome to the remainder theorem. Now to start us off, what I've done is I've written when we do a question of long division or with synthetic division, we have a polynomial of x, some power or some function of x. We divide it usually by some kind of binomial looking thing, something like this, and it gives us a quotient or an answer, which is usually another smaller function of x. And then we tack on some remainder. Okay, that's typically what we've done. And then we've rewritten it with the division statement, which says the original polynomial function could be rewritten as the divisor, the binomial, times the quotient, or the answer, plus the remainder. Now, keep in mind, these are actually equivalent. Okay, this guy here and all this stuff over here, these are actually the same functions. All I've done is rewritten it. I've reworked it. But remember, they're equal to each other. You know, this is a function of x, and this is really the same function of x. It's just been reworked into a slightly different form. So, my question is, what if I just wanted to find the remainder? What if this is what I was really interested in? You can see from our title, that's what this is all about. Well, here's a sneaky way of finding that remainder. Okay? Now, let's say I didn't work it all into this form. Let's say I was back up here, and this was my question. All I knew was I knew p of x, and I'm dividing by x minus a. So I don't know q of x, and I don't know the remainder, but this is what I want to figure out. Okay, here's the sneaky way of doing it. What if I took my polynomial function, and then I plugged in the number a, which makes this little divisor here, whoops, let's clean that up, take this little divisor and turn it into 0. Now, why would I want to do that, you might say to yourself. Okay, well, look at what happens when I plug a into this reworked side here. If I put an a in for x, then this turns to 0. Then I have 0 times the quotient. Well, all of that turns into 0, and the only thing left is r. So it's a sneaky way of finding the remainder. So in other words, I have this is given as part of the question. This is part of the question. So in order to get the remainder, all I'm going to do is say, well, what turns this into 0, and stuff it into that polynomial function. And if you look at this little breakdown over here, we should be getting the remainder. So let's do an example. So I'm just going to clear off the screen here and show you that in action. Okay. So my first example looks like this. Somebody says, we have this guy here, x squared minus 6x plus 11, and we want to divide that by x plus 1. And we don't even care about the answer. We just really were wondering what the remainder might be. I was just kind of wondering what that was. Okay, so you don't have to do the long division. I mean, why would you bother? So what I'm going to do is, well, this is the x minus a stuff over here. Okay, so what I'm going to do is say, well, what number would turn this into 0? I'm thinking -1 would turn this stuff here into 0. So I'm going to take -1 and input it into this polynomial function, right? This is the p of x stuff over here. So I'm going to plug -1 into there. So I'm going to go -1 squared minus 6 times -1 plus 11. And that's going to equal a remainder. I just got to work out what that is. So that'd be a 1. This would become a positive 6, and then plus 11, and that gives me 18. Now, I know you're probably thinking, well, why are we so interested in figuring out the remainder? But that will become very clear in the next lessons. There is a reason we want to have a quick, reliable way to figure out what the remainders are. Okay, that being said, let's do another example. So I'm going to clear off the screen here. And in this example, I'm just going to show you, sometimes they ask very mysterious looking questions. Okay, and actually the work is pretty easy once you get past the mystery. So when x cubed minus 4x squared plus kx minus 2, when we take this and we divide it by x minus 1, okay, somebody says the remainder turned out to be negative 1. So the remainder is negative 1. And what we're going to try and do is determine what k is. So determine k. Now you do a question like this, well what you do is you say to yourself, well according to the remainder theorem, what I'm going to do is figure out what turns this into 0, so that's positive 1, and then I'm going to plug positive 1 into this polynomial. So I'm going to go 1 cubed minus 4 times 1 squared plus k times 1 minus 2, and this will equal the remainder. And someone, oh, the remainder is negative 1. Oh, okay. Well, guess what I have here? I have an equation that I can solve. So if I just simplify it down a little bit, okay, let's see here. So we have 1, negative 4, and negative 2. So that makes negative 5 plus k equals negative 1. So I'm just going to add 5 to the other side, and guess what? I just solved for k. So that's one of those little bit of a different question that involves the remainder theorem, and we just plug it in and we do the math and we are there. So I'm going to stop for now and we'll talk to you later.